So the magnetic field is equal to 0. You can Taylor expand around it, and the Jacobian matrix here, the properties of that Jacobian matrix is what tells you about the relative orientation of the topological elements here, how this dome is defined, how what this is called is a spine field line, which will connect out towards like another area of the external field. We won't be talking about too much of this stuff today, but this is the process that we have in mind is reconnection in the vicinity of one of these null points and across this fan surface. That's the dome that's defined by the null point. And in that case, if you have current that is concentrated around the null, which is something that recent 3D MHD simulations have shown to happen when you stress this lower boundary, you tend to concentrate currents along these topologically important features, which is why we care about them. And when you have that, this is kind of a zoomed in view from Pontin's paper from 2012, and that's Philosophical Transactions of the Royal Society of London. But this is sort of a zoomed in around that null point. The null point is in here. This sort of grayed circular region is the region of enhanced resistivity around the null. This bundle of field lines here corresponds to this spine field line here, and these sort of diffuse ones on either side are in the area of the dome itself, the fan. And what happens is something that's a little bit interesting. In the 2D case, you had a one-to-one correspondence between field lines that gets pushed into the diffusion region and field lines that pop out. It's a one-to-one mapping between this reconnection process. But in 3D, you don't really have that. There's no way to map the field lines continuously through this diffusion region. So you need some other way to define what you mean by a reconnection rate and how to measure it. And some recent 3D MHD simulations have shown something like this. This is from a paper from Pontin, Priest, and Galsgaard in 2013, and they have again this situation. Here's the black here is negative polarity or negative magnetic field pointing down. The white is field pointing up, so the field lines are going over in this direction. You have a parasitic polarity here and a null point right there with again this sort of dome, magnetic dome topology there. And that intersects the lower boundary here in a ring. And when you perturb, when you shear the field inside of this dome, this has no flux emergence in this simulation, but what they've done is they've added a velocity field that perturbs this and adds a flow. What you find is that in this ring, this is now a top-down view, you get a region where field lines that normally were connecting in from this negative field into this positive field are now connecting out from that. So this whole boundary is shifted over, and that's how you define that reconnection. And so what I'm going to do today is go over measuring this measuring this with observations from SDO. And that's something that is good that we can do it now because we feel like I kind of pointed out, we're going to be discussing a larger case of this, spatially larger, but this sort of process happens ubiquitously and continuously on the solar surface, from very small scales up to these larger scales that we're talking about today. Moment. There's been a lot of work on this sort of thing in the past. I just mentioned a few references recently, but there's been a ton of stuff. These are related, this sort of process and reconnection around these magnetic dome regions. Yes? pokes up through the surface, sort of the dome. Something along these lines. And let's see. Right, so there's been a lot of work done on this recently. Most of it hasn't is kind of focused on very rapid events, and we're going to focus on a slower situation that takes many days rather than, 10 minutes or half an hour. I'm going to skip this. Okay, so I'm going to show this movie again. And just point out a few key things. What we want to do, what we notice here is that we have this nice dome-looking thing that we see in the EUV data. And what we want to do is overlay where that boundary is on the magnetic field data. You can see on one side of the dome we have loops. It doesn't show up maybe the best in this on this screen as always, but you see you have loops that are closing inside, and you have loops that are going over towards this other region over here, away from this. So we have this very distinct topological boundary that we can really see in the EUV data. Just show this again so you can kind of fix it in your head. And so what we'll do, again, is just define this boundary, overlay it here, find out where it lies, and look at the flux that we think it connects to. And I'd like to point out, if you watch this emergence up here, positive magnetic field, the emergence zone is right here. Positive magnetic field is pushing off in this direction to the solar west, and the negative magnetic field that's emerging is pushing up in this direction to the east and then down to the south. So there's what's nice about this is that all of this negative magnetic flux over here pre-exists the emergence. So if we see any loops that are connecting from the positive field here to the negative field on this side, we say, aha, that's an example of reconnection that we see. And that's something that we can actually measure. So I'll just let this loop through a time or two again to show the positive field pushing this direction, the negative field concentrating here and here. We're going to be looking again for the loops that are connecting over into this stuff. Well, I mean, I guess that's, I think that you see a lot of this stuff, there. There's some over there. You see this bright spot in the UV there. That's actually, unfortunately, just off the top of this image, or this movie. But that black little bit there emerges with some light stuff. There's some more that happens around. So I think this is really just kind of a constant process, and if you look at smaller scales with more detail, in the cadence here is an hour. So if you look on, shorter time scales at shorter spatial scales, you see the same sort of thing. What's nice about this one is that it's large enough and lasts for long enough that we can actually do this measurement. For these other ones, they don't last very long, and it's difficult to really make this distinction. Yeah? Yeah. Right here. You think there's a rotation in here?
Yeah.
Huh. Maybe. I'm not sure about the rotation. Maybe. There's some funny effects that go on here because you have this large negative polarity region here that kind of hangs out for the entire process. And it has a bundle of flux that sort of sweep across the top of it and cause some odd looking effects in this part of the EUV image, I think. You can really see it, this bundle there is kind of causing that blurriness, but I don't know about a rotation in here. This is, again, I mean, it's a 1 hour cadence, so I don't know. Yeah? There's also a projection from it moving across the right, because this is arc seconds from disk center, so, and this is going for multiple days. Yeah, so there may be some of that, I don't know, but I mean, there's a lot of flux that's moving here, and there's a lot of material that's being pushed out of the way. So this thing is definitely kind of carving out a space for itself, right? Because it wasn't there before, and it's there now. So it's, there's definitely a lot of motion in addition to this other reconnection that I'm going to try and be getting. Right. That's the goal. I feel like I've already said that. After we try and get this reconnected flux, I'm going to talk about how its relation to the radiated power that we measure with XRT and AIA. This is just to show that we can track these regions. This is a very coarse tracking because all I'm trying to do here is distinguish between the flux that's emerged and the flux that was already there. And the big thing to point out here, so this is just a zoomed in just on that one emergence region. And you can see I've just glommed together all negative flux and emerged negative flux because it all kind of smashes together in there, and you definitely see a big rotation around in this region as like the new flux and the old flux kind of mingle together. Let me just play this. Same with N4 is some mix of new flux and old flux that smashed together. N13 kind of breaks off on its own, and it's also some sort of mix, primarily old flux, but also some new flux. So the thing that I really wanted to concentrate on is just the flux in this N2 region, which we're pretty darn sure is all pre-existing negative flux. And so when we look for our EUV loops, we'll be looking for loops over into this region here. And that'll be our measure of how much flux is reconnected. I feel like I've kind of covered all of this. Just pointing out, I've done a topological analysis of this in a previous paper. There is a magnetic null point there. These red field lines here are separators in that fan surface of the coronal null point. So if you're into topology, well, I guess that's your thing for that. And the spine field line from this parasitic polarity pops over into this region across the large scale polarity inversion line. And it's kind of nice. This spheric boundary it actually overlays pretty darn nicely with the here's a bunch of the channels from AIA. I just wanted to point out here that you see once the dome kind of establishes itself, you see this nice dark boundary in pretty much every single EUV channel. It's nice and distinct there. The northern boundary, again, is kind of obscured by that sort of searchlight effect from that large concentration of negative polarity field above the emergence region. So it makes it hard to define the boundary in that region. We don't really trust it. But everywhere along here and around this side, the western side, we get a pretty good idea, a pretty good chance of actually distinguishing it. I also showed the 1600 angstrom data kind of down in the chromosphere. You see a lot of stuff happening in it, a lot of bright emission when it first emerges, and then a couple like spotty patches that happen continuously. And when people try and do these sorts of studies during flares, what they trace out is the ribbons in the 1600 angstrom data, overlay that on top of the magnetic field, and use that as a measure of how much flux is reconnected in a flare. It's a similar idea, but it's not quite the same in this case because there's no continual bands that you see in the 1600 angstrom data. Occasionally you do see ones right on that boundary, but a lot of this is internal. I'm not quite sure what's going on in there, but I'll pontificate about that at the end maybe. So we can define the boundary. This is the, again, the AIA 211 angstrom data. I've just run it through a high-pass filter. You get this nice, well-defined boundary after you've run it through the high-pass filter. There's our points that define this boundary. You can see the loops that are connecting, far off to this other region, the loops that connect internal to the boundary. Never the twain shall cross. And that defines this, and we can do that at every single time step. And when we do that, we get this. So on the left, I have the AIA image overlaid with the contours of the magnetic field. On the right, I have the line of sight magnetic field, or actually this is radial magnetic field with the boundary defined by the EUV data overlaid on top. Yeah, so this was using the vector field from HMI to get the radial, so I could get an actual flux. Radial relative to the surface of the sun. Yes, vertical field. But our box is pretty big. So one of the things you can see here is it advance into this region on the right. It starts off really close, and it slowly sort of gobbles up more and more flux over there on the right into this, again, this region of negative field is, we're pretty darn certain, previously, flux that predated the emergence. So any of those loops that we see over in that region are ones that we really think have reconnected with the surrounding field. And so we can sum that up at each of these time steps. Basically, take the intersection of this green curve with this blue curve that ends there. Remember, this was one of those regions that had some sort of mix of mix of new and old flux, so we're just discounting it from the data. So we just want to focus just on this region. And if we sum up all the flux between this green boundary and this blue contour there, we get stuff that looks like this. That's the red line. The black line here is the total amount of flux that has emerged. That's all the stuff in this internal contour here, all the positive flux there. So I guess it's half the emerged flux because I'm only counting the positive flux there. And the reconnected flux is this, and you can see it kind of grows over time. And then the difference between those two just gives us basically the amount of flux that's emerged that hasn't reconnected. And this is a lower bound again on that, a lower bound on the amount of flux that's reconnected over this, that's where we first are able to define the boundary. So this is over some 40 hours or something like that. So we'll focus on this red curve for just a second here. Red curve is now in black. Sorry about that. And it traces out here. This is how much of the flux that has emerged that we think is reconnected over to that other region. We can just do a linear fit to it just to get the mean amount of reconnected flux over time. And it's something like 410 to the 15 Maxwells per second. So that's just the mean reconnection rate over this 2-day period. The dashed dot line here is just the scaled amount of total flux that's emerged. That's scaled by 20.25, I think, to make it fit on the scale. We could take a ratio between those, and that's just what I plotted on the right here. So this is the percent of flux that has emerged that is reconnected. And it kind of varies between 40% and 20%, depending on when you're looking at it. The first point at which we can define this EUV boundary, so that's the first time we can get an idea of how much flux is reconnected, is about 17 hours after first emergence. This is hours since we first detect any sort of emergence in the HMI data. And the linear fit says that, according to that, it's 11 hours after first emergence before this thing does any reconnection at all. That's an interesting sort of finding in and of itself. Something pops up and doesn't immediately start it reconfiguring itself and dropping to a lower energy state. It stays in a higher energy state for half a day or so. You get similar sorts of things by other arguments. Well, I won't go into those, but other studies via very, very different methods of quiet sun emergence rate and how much total flux is in the quiet sun, you get similar sorts of things to maybe an 11-hour turnover rate in regions like this. Hagenar did some of that studies. I can't remember his first name. Another thing to point out here is that there's continual reconnection over this whole time series. But even given that continual reconnection, the amount of unreconnected flux is also growing, right? That was this blue curve, more or less growing over the time series. That becomes important in a second. I think now we're going to switch gears a little bit. So we've kind of defined this mean reconnection rate over this couple-day period. And now what we want to do is, if reconnection is happening, that's dropping from, or that's going from like a more stressed, higher energy state, and the magnetic field is giving up some of its energy and converting it into thermal energy, radiation, particle acceleration, whatever, bulk kinetic. And so we should be able to get some sort of measure of that. And so what we're going to do now, very briefly, is find irradiated power. We have XRT data that looked at this region, fortunately, over pretty much this entire time series, which doesn't always happen with XRT, so that was kind of nice. These are two of the filters from XRT. We have TiPoly, and we have the aluminum mesh filter. You could take a ratio of those of the counts in those two filters and get an emission measure and a temperature out of that, which you can use to get a radiated power as measured by XRT. There's our box. This is just showing the boundary. This was defined with the EUV data, and I've just overlaid it on top of the XRT data, which is a lot broader band. You can see it matches up nicely as you would expect. The stuff that is emitting at a lot of different wavelengths, and it's nice and co-spatial and all that. So if you're interested in this, you can look at Narukage's paper from 2011. This is just showing the radiated power. You have some sort of assumed radiative loss at a given temperature, and the emission measure at that temperature as well. I used Jim Klimchuk's and Cargill, I think that's a Peter, but I can't remember, 2011 radiative loss function. It's just of that form in order to determine what the radiated power from XRT was. You get maps that look like this. You'll notice some spots. That's because the XRT, well, there's contamination in the XRT. You can see that little dark guy, that little dark guy, that little dark guy. All those little things are spots of contamination on the CCD of XRT. So we had to mask those regions out, which made our, which means that we have kind of poor data in some of these, but you can extrapolate in from these outside boundary of each of these to recreate something like this and get an idea of how much, how much radiated power is coming out of this plasma. And in the last couple days, I used some of Joe Plowman's code to do a similar analysis using all the AIA data to get a differential emission measure and determine the radiated power as determined by AIA, so we could compare it to the XRT data. And in both cases, you get, so this is the differential emission measure, or the radiated power from AIA. Again, you can check out Joe's paper from 2013, and this is the line ratio method from XRT. So we can sum up the entire power radiated inside of this boundary in each case and get a and get the total radiated power from this dome, and we get this. The blue line is the radiated power that we get that includes all the contaminated pixels from XRT. The black line is the radiated power that we get after having filled in all of those holes in XRT and tried to interpolate what the actual radiated power is. And the red curve is the radiated power that we get from the differential emission measure analysis of AIA. They agree pretty well. They kind of scale like what you would think, if you have a bunch of zeros in your radiated power at different pixels, then your total radiated power is less. And as there's a couple spiky bits that happen in here. That's little small scale, flashy, probably small scale reconnection that happens over the time series. What's interesting is those spikes don't really correlate with any sudden jump in the boundary. So they don't appear to be like going with reconnection to the external field. That appears to be some sort of internal process that's going on. And we're really focused on how much power is, or how much reconnection is going on with the external field. And so integrated over the entire time series, you get something like almost 10 to the 31 ergs of energy that this thing is lost due to radiation over the time series. That's quite a bit. That's what you might get in a large M-class or a small X-class flare. But this is spread out over, you know, over 40 hours or so. And the amount of reconnection that you get that we measure is, again, of order what you get in a large M-class or small X-class flare, but spread out over 40 hours instead of concentrated into half an hour like you would see in a flare. You'll notice that the right-hand scale of this is in amps, and that's because I took the power and I divided it by the mean reconnection rate, and that has units of current. Guess it actually, in Gaussian units, it's 10 amps, but once you do the conversion. What that is if the radiated power is all due to reconnection across the current sheet at the given EMF, then that's the net current in the current sheet that you're moving this flux across. So it's basically, it's a measure of the net current in the current sheet that we think is actually there. Now, you don't immediately dump all of your energy loss from this reconnection into radiated power, so it's a lower bound on the current in the current sheet in that regard. But at the same time, our mean reconnection rate is probably a lower bound as well. So those kind of compete with each other, and that's a little bit difficult to I guess give a further pin down of what that might be, that current. On the other hand, you can only reconnect up to 100% of the emerged flux. So you could multiply that current by a factor of 2 to 4 at max, because we're anywhere between 20 and 40% of the total amount of flux is reconnected at any time. So speaking of that unreconnected flux, we can also scale the unreconnected flux to the radiated power. So here what we have is the total flux that is emerged and minus the flux that we think is reconnected, and that gives us the amount of flux that hasn't been reconnected. And if we multiply that by some number with appropriate units, we get a power. And that's what I've shown here with this this blue and this red curve is the unreconnected flux scaled to the power, the radiated power that we get from XRT, and the unreconnected flux scaled to the power, radiated power that we get with AIA. I haven't plotted the AIA radiated power on this again, just to make it too cluttered. In that scaling factor X, well, what do we have here? We have a current and we have a flux, and we've multiplied by some scaling factor between current and flux, and that's by definition an inductance, which is related to energy. Basically what we're saying in here is that this current that we've measured is the current that's required to keep this flux from reconnecting. It has units of length, and the scaling factor that you get is something of order, well, it turns out to be something like 30 megameters, which is pretty interesting because it's not grossly different than the actual length scale of this dome that we're talking about. And that's kind of odd because it implies a reconnection electric field is something like around 1 volt per meter, which is insane, right? If you have an electric field of a volt per meter and it's acting over, 30 megameters, you should be getting crazy, insane energies out of this thing, that you might see like giga-electron volt accelerated electrons or something like that, that you would observe with RESI, but you don't see anything like that. And what's also interesting about this is this sort of reconnection electric field, you get this same order of electric field when you do a similar type of analysis, but during flares. So that's looking at the flare ribbons and 1600 angstrom data, overlaying it on top of the magnetic field data, getting a total amount of radiated power and a total amount of reconnected flux in a flare in that 30-minute period. You get the same sorts of numbers out of it. So that presents somewhat of a conundrum, right? Because again, if you trust the radiated power from this thing and you trust the reconnected amount of flux, I mean that sort of number is inevitable. But what I think is going on here is probably something more like this. The total radiated power is really the sum of some internal processes that are going on in emergence in addition to this external reconnection. And I don't know how well this will transfer over into the case of flares. I haven't thought about it very much, but you could break that internal processes that are causing this radiated power maybe into some form of wave heating, MHD wave heating, where the MHD waves have gotten trapped within this magnetic dome, though maybe that's pretty inefficient because it's hard to trap MHD waves like that, apparently, or possibly some sort of radiated power that's due to a bunch of internal reconnection in some sort of Taylor relaxation type process. No, I don't mean the interior of the sun, I mean inside the dome. Well, this is I don't mean it by internal and external. I mean internal processes internal to the dome that is causing transfer of, say, magnetic processes, and by external, what I mean is the interaction. What I mean by external. Does that make sense? So imagine you have one of these tubes popping up, but instead of some ability to reconfigure itself, it also has some act across the boundary. What's just been newly emergent measured is that, this P external, this power external that I'm talking about, is that reconnection at the outer boundary. I guess my point in saying this is that I assumed that P total was only that external, only due to this sort of mean EMF and this acting across this current sheet of net current I. But there's probably also these other processes going on that we don't have a good measure of. And so I guess that's really where I'm going with this and where I'm ending it right now is that's kind of the next step, is to try and see, well, can I figure out maybe how much wave heating is going on inside from sloshing around inside of this emerging feature, how much internal reconnection might be going on that's causing radiated emission from this, and then I can get a fix on how much, what our actual current and what our actual kind of net current that's dividing these two systems is. there's my summary. Right, we studied one example in detail. We get an average reconnection rate of something like that for 40 hours. There's this weird lag that goes for about half a day between when it first emerges and when we can detect its first reconnection with the external field. At any given time, something like 20 to 40% of all the flux that has emerged we think is reconnected with the surrounding field. And at the same time, kind of, maybe I should put a big line right there, we also get some sort of radiated power, something like 2 to 8, 10 to the 25 ergs per second, that's steadily growing over this couple day period. When you combine that with that, you get a current, in quotes, of something like 210 to the 11 amps that has, that gives you something like a volt per meter electric field and also some sort of characteristic inductive length of 30 megameters, which is the size of the structure that we're talking about. And what I said on the last slide is that, we're clearly missing something in that, because that electric field, that reconnection electric field that you get out of this and you get out of other similar type studies just can't be correct. Right. And the last sort of thing is, it's like a small X-class flare that takes 50 hours instead of 30 minutes too. So there's that whole other question of, why is this thing kind of continually going on for such a long period of time? Why doesn't it happen all at once? Why does it have a lag? Why does it have a lag of 12 hours? Those are all sort of questions that crop up at the end of this analysis. So study those sorts of things in the future. Thank you. I hope I didn't get grossly over time.
Well, not at all. Thank you very much for staying behind me that we started later. And thank you very much for turning a bunch of quantities that spoke a variety of questions. So on that, do we have any questions? Yeah, you want? What?
Yeah, I mean, you don't even really need to do an extrapolation to figure it out in this case, right? You have all this black negative field and positive field, so it's all going like that, angle like that, and then inside the dome, you have that, right? So your angle is something like 30 degrees at the location of the null point. It doesn't appear to be perfectly aligned like that. This filament doesn't do anything during this process. And there's a flare, there's an M3 flare that happens at the very end of my data, well, just after I stop this analysis. And so there's an M3 flare, which is pretty decent sized flare, one of the largest ones up to date, captured. And that filament, which is huge right there, also just does nothing during that eruption. So that's an interesting thing.
Another question about the complex field. I'm trying to visualize, you talked about the energy vector, what happens to the radiation. What the heck happens to the magnetic topology? You have this dome emerging, you have a lot of reconnection, and also above the corona. Does that mean that you form isolated magnetic bubbles above the photosphere?
Oh, no, so
You're reconnecting foot points, essentially.
You end up with something along the lines of what Pontin, Priest, and Galsgaard really, let's see, a lot of these papers doing 3D MHD are with Galsgaard here, and only one of them involves emergence, unfortunately, because it's hard to do. but it's just starting to be done in trying to measure a reconnection in that sort of sense. But I think you always end up with this sort of a thing where, you know, here's your dome, you have reconnection in the vicinity of this null point here, and you get a broad swapping of field lines that are originally connected inside, going and connecting outside, and then, you know, the opposite at other parts of this ring, where they used to be connected outside and now they're connected to the internal field. This is again done with just shearing in the vicinity of field lines that connect, you know, pretty directly up to that null point. But you're going to get the similar sort of thing, I think, when you have flux emergence. And of course, in the case that we're looking at here, we have flux emergence and shear, right? There's a ton of shear in this system I'm looking at. You can't really disentangle those two effects in that case.
Right, and the other question is your 40% number of reconnected flux. That's going to vary a lot from event to event, isn't it, depending on what the existing field is, or is it?
Gee, I'd say eventually it's probably going to always end up at 100%. Right? But I don't know how that one will vary. You know, we can study it in this case. What I have in mind a lot of the time is these sort of X-ray jets and bright points. And I don't think you can quite do this type of study with that case. You can't get the boundary well defined enough and overlay it on the magnetic field and get an accurate, like even a semi-accurate measure of how much flux is reconnected in that case for these smaller events. So I kind of have to do this by analogy, right? For at least in my mind, thinking about smaller events like that.